So far in the NMR spectroscopy course, we have learned how to use the theory where we calculate density matrices as a function of the pulse sequences that we design to help us get the desired result. We were able to exemplify this with the help of the distortionless enhancement by polarization transfer, which helped you obtain a 13C1D NMR which has CH, CH2, CH3 spectral editing that is possible. Similarly, as we go forward, we will now try to understand how NMR spectroscopy could actually help you get even more information at a much higher resolution. One of the commonly applied extensions of NMR spectroscopy is acquiring data in a multidimensional fashion. Before going ahead to understand what is multidimensional NMR, in this lecture we will try to set the stage for understanding why we need multidimensional NMR experiments. In order to understand this, I'm just going to give you some simple examples to start with. The main parameters that you're really interested to obtain in an NMR experiment is the proton chemical shift, followed by the magnitude of scalar coupling and its associated multiplicity, meaning singlet, doublet, triplet, followed by integrals that help you understand how many protons are present in the system that you're interrogating. However, you could end up in a case where the proton chemical shifts overlap due to several reasons. If you might recollect, what gives a rise to chemical shifts is the electronic environment around a given spin. What could happen is that multiple effects could play a role such that proton resonance overlap might end up coming. In order to still assign such protons at atomic resolution, you need other complementary information. In order to exemplify this example, I'm going to take the help of flowers. You might ask why flowers? Because everybody would have seen it, and the example would help you understand how the complementariness would play a role in understanding and classifying flowers. This is an illustration of a flower, and you also have the various features of flowers listed here. For instance, the petal. Petal is something that we end up noticing most often in a flower, which is colorful. And you also have other features such as the sepal, pedicle, style, ovary, stigma, and many other parts of the flower. Now let us take the problem of classifying flowers. You're able to understand various features are present. We could classify flowers based on the colors of the petals, which is straightforward for us because we perceive color. Number of petals that are present in a given flower. You are able to see different flowers as shown here, and you are able to understand the colors are quite different. Here you see a violet lavender color, here you see a yellow color, orangish red, a nice rose, purple, and a pale orange, yellow, and white color. And what you're able to understand, therefore, if I take the color as the classification, all these 9 flowers would be clearly classified in such an example. Let me take another example here. And in this example, what you're able to understand, some of the flowers are the same color of the petal. So unlike the previous classification where a color of the petal helped you distinguish all the 9 flowers that you are interrogating, in this case, if you start using the color of the petal, you are able to understand there's a lot of degeneracy. For instance, the 4 flowers that are being circled right now have white petals, and the other 4 flowers that are being currently circled have yellow petals. The remaining 2 have something very close to purple violet, and the only one on blue. So now what this causes as a complication is that although colors was quite effective in distinguishing flowers from the previous set, in this set you are able to understand the colors are not the only parameter that would help you define every flower individually. So in that aspect, if we start to use yet another variable which is complementary to color, in this case we can take the number of petals. You are able to understand here you have a single petal, right bottommost, and here you have something like 1, 2, 3, 4, 5, 6 petals, and here also you have 6 petals. In this case you have 5 petals. What has happened is that in addition to the color of the petals, if you take the number of petals, you are able to understand out of the 4 white flowers, you are able to get 3 very well classified entities. Only the 2 other ones which have the same number of petals are degenerate. Now, let's say you add yet another dimensionality to it where you try to take the surface area of a given petal, you would be able to understand the bottom leftmost flower and the top leftmost flower would be distinguishable. Similarly, applying the number of petals for the yellow flowers also helps you distinguish each of the flower individually, similar to the aspect of the purple flowers that you're trying to look at. I hope this example helped you understand if different features of the flowers are used, it would help towards classifying them when you have a bunch of flowers. So similar is multidimensional NMR spectroscopy, where in addition to the proton chemical shift, if you are able to correlate with carbon chemical shift, or for that matter nitrogen chemical shift, it will help you determine some of the peaks that are overlapped in the proton region. Or you can also use complementary parameters such as scalar coupling or the distances with respect to other protons that are nearby, or for that matter go with other physical parameters such as translational diffusion coefficient. So in this way, what you would end up happening, the proton resonances that are overlapped would get an additional dimension such that these two protons might get resolved in yet another dimension. So we'll take an example of this, paying close attention to what happens in biomolecules. Why multidimensional NMR experiments are critical for studying biomolecules. Here you're seeing the proton NMR spectrum of sucrose. Sucrose is C12H22O11. And there are a few things that you're able to observe straight out of the bat for the small molecule, which is about 342 Dalton in its molecular weight. You're able to understand that the proton resonances are sharp, which gives you very narrow resonances. You have seen this example in the case of camphor earlier in this course. And if you zoom into this region, you will also appreciate the fact the multiplicity is very well visible, meaning that the resolution that the resonances are, where the peaks have a half width to the tune of half a hertz, are able to show the multiplicity quite clearly. That helps you assign each of the 22 protons easily. And what you are seeing to your right hand side right now is a protein called bovine pancreatic trypsin inhibitor. This is a 55 amino acid protein that has been extensively characterized, and in fact is the first protein structure to have been solved using solution-state NMR spectroscopy. 55 amino acids imply that its molecular weight is around 65 kilodalton. And here, once again, you're talking about a system that has 284 carbon atoms, 438 protons, 84 nitrogen atoms, 79 oxygen atoms, and 7 sulfur atoms. The one immediate thing that you are able to understand is that the number of resonances are going to increase because the number of protons has increased tremendously. And in addition, we will also be seeing other effects that accompany when you go from small molecule to large molecules while you characterize using solution-state NMR spectroscopy. You are able to see the proton NMR spectrum between 1 to 10 ppm predominantly. Of course, some of the resonances go much more downfield than 0 ppm. That's largely because some protons that are present in the interior, that is the core of the protein, end up experiencing more deshielding effect to come up in resonances that are less than 0 ppm. And as always, the aliphatic protons come in 0 to 5-6 ppm, and the aromatic and the amide protons end up coming little downfield, as shown here. Downfield with respect to water. Water ends up coming here. Water is suppressed, therefore you don't see the water resonance. And this is generally, these kind of experiments are generally done in 90% H2O with 10% D2O used for field frequency lock-in. And immediately you are able to understand the 438 protons that are present cannot be easily observed from this itself. So let me once again summarize some of the aspects that we have learned. So the important take-home message here is that the number of resonances increase, and on top of it, line widths are also much broader than that of what you observed for sucrose, which is a small molecule, resulting in the fact that the proton chemical shift by itself cannot help you resolve all the resonances that you want to assign in this molecule. So why don't we divide and conquer this problem? Let's say this is the proton NMR spectrum, and in some way you are able to get an orthogonal data set that will help you assign these protons. So that is what is done in the 2D NMR spectrum here. And what you are able to see is that you are correlating 13C spins with 1H, and in the indirect dimension, we will call it the F1 dimension. The direct dimension is called the F2 dimension. is that you are able to see that the chemical shift of carbon is encoded in addition to the chemical shift of proton. For instance, I've just circled the proton here, and if you see, there are many protons that end up having their overlap resolved by the carbon resonances. I don't have to exemplify any further. This helps you understand how an additional data set would help you assign something for a biomolecule. Similar is the case when you go downfield. In this case, we see a 13C1H spectrum, but at the same time, you can also get a 15N1H heteronuclear correlation spectrum that helps you resolve the amide resonances that are present. For audience who might not be comfortable with amino acids, basically you're looking at a backbone of a polymer that looks like this. This is the amide part of it, which is being plotted here, the amino protons that are present and resolved by the nitrogen chemical shift for the protein BPTI that we are trying to study using solution-state NMR spectroscopy. I hope this helps you understand how a two-dimensional spectrum would help you alleviate resonances that are severely overlapped in the proton NMR spectrum. Going forward, for protein studies, it's quite common to get the nitrogen proton two-dimensional correlation spectrum in order to study them. Here, you're seeing the heteronuclear correlation spectrum of another very well-studied protein called ubiquitin, which has 76 residues. The primary sequence of this protein is given below, and the important things that you got to take home from here is that for any protein, the nitrogen proton heteronuclear correlation spectrum is like a fingerprint, meaning that it's quite unique for a protein that has a given certain fold, largely because in this case, you are able to see this protein has alpha helices and beta sheets. Once again, for the audience who might not know what these secondary structures are, alpha helices are secondary structure elements where the I and the I plus fourth residue, which is the monomer, ends up having a hydrogen bonding partner. And on the other hand, you also see arrows that are shown here. These are called beta pleated sheets, which end up also having hydrogen bonding partners, but not in the I and I plus 4, but based on the strands that they are present in. And if you recollect, the proline residue does not have an amino proton following the polymerization. So therefore, the three proline residues that are present in this protein ubiquitin will not be observable in the NH correlation spectrum. But otherwise, you would end up seeing one NH resonance like this for each amino acid that is present. So in theory, if you have a 76 residue protein, you're expecting 76 minus 3, where 3 are prolines, about 73 peaks that are going to be present. In addition to the NH, in this case, you'll also see NH2 resonances that come from asparagine and glutamine residues. These have a CONH2, and this NH2 residues for a given nitrogen chemical shift, you see two proton resonances that are present. Just as we had discussed earlier for two proteins, BPT and ubiquitin, how the NH-HSQC looks, this is an example where a protein called hahelin, which is 92 residues, once again the primary sequence given at the bottom, is composed of alpha helices and beta sheet when it is in the folded form. Interestingly enough, the apo form of this protein, meaning that the one that is in absence of the ligand, is actually unfolded in nature. The spectrum for the unfolded protein is given in the B subset of this figure, and there are a few observations that you are able to make. The first observation that comes to your head is that the proton resonances are poorly dispersed. Dispersed meaning the chemical shift range that is sampled in an unfolded form is very narrow. So due to this case, you are once again able to understand that these kind of systems cannot be studied just using proton NMR spectroscopy. And of course, this is the CONH2 region that we had discussed earlier for asparagine and glutamine. But at the same time, you are also able to appreciate the fact that the nitrogen chemical shift is fairly well resolved. So therefore, the complementariness that's provided by the nitrogen chemical shift helps you characterize even the unfolded state of this protein hahelin. In fact, nowadays this has become a common practice to study protein systems called intrinsically disordered proteins that do not have an inherent structure and sample microstates that are present, and NMR spectroscopy allows you to understand what are their structural preferences in the solution state. On the other hand, when the calcium is thrown into the sample, immediately you are able to see the heteronuclear correlation spectrum changes drastically. You are able to understand the proton chemical shift becomes much more well dispersed, and the nitrogen chemical shift also improves a little bit. And if you sit and calmly count again, you're going to count about 90 residues that are going to be present. I'd like to point out a few more important observations here. In this case, the more the number of aromatic residues that are present, I'm just circling the phenylalanine and tyrosine residues since this protein does not have a tryptophan, which is given the alphabet W. You are able to see the proton dispersion is much more, meaning that the chemical shifts that are sampled are between, say, 6 ppm and 10 ppm. On the other hand, if you go back to the case of ubiquitin, you are able to see it spans about 6.5 ppm and to something like 9.5 ppm, largely because the number of aromatic residues are significantly lesser. In ubiquitin, you have a tyrosine and probably you have a few phenylalanines that are present. So this gives you a very good understanding that if your protein does have a number of aromatic residues and is well folded, will give you a beautiful 15N proton correlation spectrum that will help you characterize the systems as we go forward. These examples already give you an idea that a one-dimensional NMR experiment is completely inhibited. However, on the other hand, when you're able to do two-dimensional NMR spectroscopy, you are able to get higher information for the systems that you're studying. Just to go a little bit more in details, one can also perform binding studies where the chemical shifts can be monitored as a function of another entity that is added to the sample. In this case, they are studying a protein-protein interaction of a protein that is TAS2 is studied along with AD1P53 domain. And what you are able to understand is certain specific residue C1827, which is a cysteine, is undergoing chemical shift perturbations upon addition of the other protein. Without going into much details, it's quite interesting how much information such two-dimensional correlation spectrum could give. If you end up seeing a trajectory that is non-linear, this already indicates intermediate states could be present in such binding processes. On the other hand, if you end up seeing a linear line, as you see in this case, it could indicate that that given residue does not sample any intermediate states while the binding goes on. And once again, you are also able to see a similar effect here where C1828 is also seeing a non-linear trajectory. These kind of studies would help one understand how the binding of the AD1 domain goes with the TAS2 domain. Further and more closer analysis could be done where as a function of the titrant concentration, you could follow the proton and nitrogen chemical shift, which helps you understand which set of residues bind first, followed by the other set of residues that come in. Such an analysis would help you understand which parts of the proteins are first bound by the other protein and how the protein-protein complex formation could happen. So far, the examples that have been illustrated here are all equilibrium studies. So what about kinetic experiments? This is an example once again of the protein ubiquitin for which the 15N1H correlation spectrum was obtained as a function of time when the sample was changed from a H2O rich to a D2O rich solution. The whole idea behind this is one where the NH will get exchanged to ND, therefore will cause the loss of a resonance from this two-dimensional correlation spectrum, indicating the fact whichever residues get exchanged first are more exposed to the solvent, while the ones that take a longer time to get exchanged would be present in the secondary structure elements. And here they were able to record a spectrum for every 5 seconds in order to understand how this protein ends up behaving. Such fast measurements have also been performed for larger protein systems and with reasonable concentrations of 0.5 to 1 millimolar samples, which are 15N and C13 enriched. This slide helps you understand not just how nitrogen 15 chemical shifts help, also C13 help you distinguish in different aspects of the protein. Just to go back to the detail, you have a H alpha that is present and an alkyl group that is different depending upon the type of amino acid that you are referring to. And here you are able to understand the carbon chemical shifts and proton chemical shifts for the alpha beta carbons are quite different depending upon the amino acid that you're talking about. Let's take a simple example here of alanine versus phenylalanine, where phenylalanine is nothing but an extra phenyl group that is present to the alanine amino acid. So when you pay attention here, you are able to understand that the beta carbon, this is the beta carbon in both the cases, you're able to understand that the beta carbon for the phenylalanine is much more downfield in comparison to the alanine residue. And of course, these are all ranges that are given with the standard deviation. Similarly, you can also see the proton chemical shifts. And as you go for residues that have a lot more aliphatic groups, there are more overlap that end up coming, which are nicely resolved by the carbon spectrum when acquired. These are just not the cases for proteins, but also for nucleic acids, where you end up seeing an AT or an AU base pair followed by a GC base pair in DNA and RNA. This is a characteristic region of the proton resonances where you end up seeing chemical shifts of iminoprotons. By iminoprotons, we mean this for the thymine. And when they are hydrogen bonded, they end up coming between 13 to 14 ppm. This is not just for the AT. The AT is given as an example here. This is acquired for a 12-mer DNA duplex. I'm trying to illustrate an example where when one of the residue is actually switched from a Watson and Crick base pairing to an alternate base pairing called Hookstein base pairing, with the iminoproton being exactly the same, only with the fact that the side chain of the adenine gets changed from anti to syn, you're able to understand one given resonance, which is T9, which is what is changed from a Watson Crick to Hookstein. The chemical shift changes tremendously, although it is indeed the same spin that you're trying to follow. So this gives you an understanding on how chemical shifts are extremely sensitive parameters in order to observe any changes that happen in a biomolecule. It doesn't stop here. For RNA, there are even more differences that come up with respect to a duplex DNA, where pairs such as GU, UU, and GA are also commonly found. And once again, you are able to understand from the proton chemical shift how these could be quite different, and with addition of the nitrogen chemical shift, how each of this could help you assign what type of such mispairs are present in your RNA system. Okay, all this is quite interesting, but let's talk about the fact, why did the line width increase? I'm sure from the earlier lectures you would remember the full width at half height is proportional to the transverse relaxation rate R2, which in turn is proportional to the isotropic tumbling time, that is tau c, which once again is proportional to the size of the molecule. In this case, the radius of the molecule. We are assuming it's a sphere. For the sake of simplicity, this helps us in our understanding. As the molecular weight increases, the molecular size increases. So therefore, the radius increases, which in turn increases the tau c, resulting in very broad resonances. If you might remember, we started with the fact of sucrose versus BPTI, where the resonances in BPTI were very much more broader than that of sucrose. And this is the reason that causes line widths to increase. And immediately you are able to understand molecular size poses a severe limitation on NMR spectroscopy, that if the lines become too broad, you might not end up seeing the resonance. This is indeed a limitation for solution-state NMR spectroscopy, where predominantly people look for protein of the sizes of 25 kilodalton as a ballpark range, and with additional specific labeling, people can go up to 50 kilodalton. However, there have been new methods that have come up to alleviate such resonance overlap and larger size limitations. Without going into much detail, this experiment is called the transverse relaxation optimized spectroscopy, where on the right hand side you look at the conventional NMR experiment that results in very broad resonances for a protein which has 405 amino acids. You're talking about something to the tune of 45 kilodalton. And when the Strozzi experiment is applied, resonances are much more well resolved and are much more sharper. Similar advancements have also been found where the molecular size limit has been pushed even to megadalton sizes. Here you are able to see an example where the methyl groups of isoleucine and valine and leucine have been specifically labeled such that all its neighboring partners are deuterated. The moment they are deuterated, these methyl groups have favorable relaxation properties such that even very large sized proteins can be studied using this methodology. In fact, this is the transverse relaxation optimized spectroscopy for methyl groups, which help you study systems that are really big. With this being the premise, I hope this has established a clear understanding that A multidimensional NMR experiment is indispensable in trying to characterize biomolecules such as proteins and nucleic acids.